The Oregon State Mars Rover team is proud to exhibit our most advanced, capable, and reliable rover to date. We have further developed and refined our systems to tackle this year's URC competition tasks. For the equipment servicing task, our rover will be outfitted with a 6 degree of freedom arm and grasping end effector. Our arm has encoders and strain wave gearboxes at each joint to provide accurate positional feedback and reduce backlash. A camera, distance sensor, laser, and force sensor integrated into the gripper relay situational data back to the base station. The gripper and the arm will be controlled as part of a larger RS-485 communication network, running a custom, reliable signal protocol based on Modbus. We've practiced on equipment servicing mock-ups to ensure our team is competition ready. Our arm can lift and transport heavy objects, as well as manipulate handles and joysticks. Our gripper geometry keeps the fingertips parallel throughout the entire grasping range, allowing it to perform precise actions, such as tightening a screw, flipping switches, and plugging in a USB stick. To further improve the robot's capability in dexterous tasks, we're developing inverse kinematics, allowing the operator to focus on the position of the gripper in 3D space, instead of positioning each joint individually. Our modified rocker bogie geometry maximizes the number of wheels in contact with drive surfaces to ensure the rover can surmount uneven terrain and large obstacles. The low-pressure pneumatic wheels and custom rubber tread increase traction and conform to rough topography. An IMU in the electronics box provides pitch and roll positions to the operators to ensure the rover is operating in a safe orientation. We have 3 cameras, with active resolution adjustment based on available bandwidth, located on the tower, at the front of the chassis, and underneath the E-box, to provide multiple perspectives of the rover's environment. Our Ubiquiti Rocket M2 radio has been tested at ranges over 1 kilometer with line of sight and up to 800 meters non-line of sight, allowing us to relay critical systems information remotely to our base station. In its full competition configuration, the rover can drive over harsh terrain and operate the arm even in challenging positions. Our rover uses RGBD SLAM and dual extended Kalman filtering for transforming and fusing odometry sources for autonomous navigation. It is equipped with a Z stereoscopic camera for visual odometry, an IMU for absolute orientation, a GPS for locational accuracy, and encoders for wheel odometry. These devices are currently being integrated to work cohesively to provide the necessary odometry data for waypoint navigation, obstacle detection, and object avoidance. Waypoints are initially entered from the base station and are then buffered for global path planning. Our Z can detect and track AR tags from up to 6.6 meters away. It can generate a point cloud and occupancy grid for obstacles up to 10 meters away. Our science mechanism performs in situ tests to determine the habitability and presence of life at numerous locations. The mechanism shown is in the first version and will be fully tested by competition. The sensor array contains a soil health probe, pH probe, microscope, and spectrometer used to analyze sample locations. The sensor array is attached to a linear motion system descending to allow soil penetration during testing. A wire brush is used to disrupt the soil, and a vacuum obtains and deposits the soil into a central reservoir. The soil is measured and delivered into divided cups through a rotary feeder valve attached to a continuous rotation servo. Unused soil is disposed of in a waste bin, limiting cross-contamination between samples and the environment. After soil collection, the cups are rotated to a live feed FPV camera, where burette and Lugol's iodine solution are added through a solenoid-controlled system. Lugol's iodine and burette solution identify starches and proteins, which are primary building blocks in humans and other biotic organisms. After the experiments are conducted, the main point-and-shoot camera is used to capture the color concentration of the solutions, which identify the presence of life. Atmospheric data observed from wind, dust, UV radiation, air quality, and temperature sensors supplements the experimental data. Data from the geologic and atmospheric sensors, along with the biological experiments at each of the sites, is transmitted to the base station and combined into a point-based algorithm. This algorithm determines biologic life presence, as well as habitability for each location. These new features will be further tested and improved in the coming months. We look forward to challenging ourselves at URC 2020.